We'll begin in 1 minute. Today we'll continue with the Test 3 review. The Test 3 is this Friday. The Quiz 11 Moodle assignment is also due on Friday at midnight. So let's continue the Test 3 review. So I won't do every single problem I have on these sheets so that we can get a representative of the problems. But we will graph this function, y equals log base 3 of x plus 1. Notice that the argument x plus 1 has to be greater than 0, so the domain is x greater than -1. So in interval notation, the domain is parenthesis -1 comma infinity. And we want to pick some ordered pairs of points that are on the graph. The vertical line x equals -1 is a vertical asymptote. Okay, but if I pick a few x values strategically, if I pick x to be -8/9, then replace x in the function with -8/9. -8/9 plus 1 is 1/9, and log base 3 of 1/9 is equal to -2. Then if I pick an x value -2/3, and in the function replace x with -2/3, -2/3 plus 1 is 1/3, and log base 3 of 1/3 is equal to -1. Then if I pick x to be 0, log base 3 of 0 plus 1, or log base 3 of 1 equals 0, because 3 to the 0 equals 1. And then the other x values will be easier. If I pick x to be 2, log base 3 of 2 plus 1, or log base 3 of 3 equals 1. Then I probably won't plot this point, but if you pick x to be 8, and then in the function replace x with 8, we get log base 3 of 9, because 8 plus 1 is 9. Log base 3 of 9 is 2. Okay, so we'll plot those points. So the vertical line below the x-axis, x equals -1, is a vertical asymptote. Okay, so -8/9, -2. It's about right there. -2/3, -1. The point 0, 0 is an x-intercept and a y-intercept. When x is 2, the output is 1. So this is not too bad of a graph. So I'll label those points. That one's 2, 1, 0, 0. Yeah, that's pretty good. Now let's find the inverse. So I'll just rewrite y equals log base 3 of x plus 1. Interchange x and y, so x equals log base 3 of y plus 1. And then convert this logarithmic equation into its exponential equation equivalent. 3 raised to the exponent x equals y plus 1. So I'll put y plus 1 equals 3 to the x, and then subtract 1 from both sides. Y equals 3 to the x minus 1. So just one thing to observe: x equals -1 below the x-axis is a vertical asymptote for the logarithmic function, and its inverse has a horizontal asymptote at y equals -1. So it's not a coincidence that those numbers are the same. When we find the inverse of a function, we interchange x and y. So that's why this is a horizontal asymptote for the exponential function y equals 3 to the x minus 1. Okay, next we'll simplify some logarithmic expressions. The directions might also say evaluate. Okay, so this one we're adding 2 base 5 logarithms, so that means we can write a single base 5 logarithm if we multiply the arguments, so 25/3 times 75, and 3 goes into 75 25 times, So this is log base 3 of 25 times 25, or log base 3 of 625. Sorry, not base 3. These are base 5 logarithms. Okay, so log base 5 of 625 is equal to 4 because 5 to the 4th equals 625. Okay, the next example, log base 6 of 216 minus log base 6 of 6. So since we're subtracting a base 6 logarithm from the other, we can write it as a single base 6 logarithm if we divide the argument 216 by 6. And 206, stuck on 3. So 216 divided by 6 is 36. And log base 6 of 36 equals 2 because 6 to the 2nd power equals 36. Okay, in the next example, for now we'll just do part A. And then if there's time, we'll come back and do the part B. But this says compress each expression to a single logarithm with coefficient 1. So you might not always see the word compress, but it just means to write, using properties of logarithms, write this into a single logarithm with coefficient 1. So that means on this first one, we have to move the coefficient 3 to the position of the exponent. So this is equivalent to log base 2 of the binomial x plus 2 to the 3rd. And then we have minus, we're going to move the coefficient 2 to the position of the exponent. So we'll have minus log base 2 of the quantity x squared plus 4 squared. And for now, this third logarithm just stays the way it is, log base 2 of x. Okay, so what we can do in the next step, since we're subtracting log base 2 of the quantity x squared plus 4 to the 2nd, we'll put this argument in the denominator, and since we're adding log base 2 of x, we'll put a factor of x in the numerator. So when we write it as a single base 2 logarithm, we'll have in the numerator x plus 2 quantity to the 3rd multiplied by x, and then in the denominator we have x squared plus 4 to the 2nd. And don't do any more with that argument. This is all that's expected. Okay, we'll move down here to problem number 6, where we do the opposite thing. Here we're starting with a base 3 logarithm with a coefficient of 1, and we want to expand it as much as possible. So since we have log base 3 of a quotient, log base 3 of x squared minus 25 over x plus 7, we can write this as log base 3 of x squared minus 25 minus log base 3 of x plus 7. The x squared minus 25 is a difference of squares, so we can factor that. So we'll rewrite that log base 3 of x minus 5 times x plus 5, and then minus log base 3 of x plus 7. And then the last step, since we have a product in this argument, we'll rewrite this as a sum of 2 base 3 logarithms. So one is log base 3 of x minus 5, and then we're adding that to the base 3 logarithm of x plus 5, and then we're subtracting log base 3 of x plus 7. So this is the expanded form that we want on this one. Okay, we'll solve some equations, exponential equations, and then a little bit later we'll solve some logarithmic equations. So this one, 5 to the x plus 2 equals 4 to the 3x minus 1. We want to solve for x. We see that x is in each of two exponents. So we'll use a logarithm to get x out of the exponent. We often just use the natural log. So take the natural log of both sides. The natural log of 5 to the x plus 2 equals the natural log of 4 to the 3x minus 1. And then one of the properties of logarithms says we can bring the exponent of the argument to the front, so it's x plus 2 times the natural log of 5. And we'll do the same thing on the right-hand side. The exponent 3x minus 1, we bring that entire binomial out front and write it as 3x minus 1 times the natural log of 4. The goal is to solve for x. So we'll apply the distributive property on each side. On the left-hand side, we have x times the natural log of 5 plus 2 times the natural log of 5. On the right-hand side, 3x times the natural log of 4 minus the natural log of 4. We're solving for x. Two of the terms have x in it. We want those terms on the same side of the equation, and every other term that doesn't have x on the other side. So what I'm going to do, I'm going to add the natural log of 4 to both sides and subtract x times the natural log of 5 from both sides. So when I add the natural log of 4, I get the natural log of 4 on the left-hand side plus 2 times the natural log of 5. And then on the right-hand side, I already have 3x times the natural log of 4, but I'm subtracting x times the natural log of 5. Okay, now that every term with x is on the left-hand side, I can factor x out. So up here I'll write the left-hand side. It's the natural log of 4 plus 2 times the natural log of 5. And we're factoring x out of each of the two terms on the right-hand side down here. So it's x times 3 times the natural log of 4 minus the natural log of 5. Okay, and now we're just one step away. So divide both sides by 3 times the natural log of 4 minus the natural log of 5. So the solution for x is the natural log of 4 plus 2 times the natural log of 5, all divided by 3 times the natural log of 4 minus the natural log of 5. That's equal to x. Okay, we'll go ahead and solve the next equation. 0.7 raised to the exponent x plus 2 equals 3.8. To start with, subtract 2 from both sides, so we get 0.7 raised to the exponent x equals 1.8. X is in the exponent, so we get the variable out of the exponent by using a logarithm. So we'll just take the natural log of both sides. The natural log of 0.7 to the x equals the natural log of 1.8. The reason we're using a logarithm is so we can get x out of the exponent. So we can move the exponent x in this argument out front, so it's x times the natural log of 0.7 equals the natural log of 1.8. And then the last thing we do is divide both sides by the natural log of 0.7. So x is equal to the natural log of 1.8 divided by the natural log of 0.7. So this is what is referred to as an exact answer for Friday's test. Exact answers are really all you need to do. You can take the time to convert it to a decimal number, but it might be time that's not really necessary to spend converting it to a decimal on a test. Just be able to do it on the final exam if it's ever asked for you to convert it to a decimal on the final. Okay, the next equation is a logarithmic equation. Log base 2 of x plus log base 2 of x plus 2 equals 3. The first thing we do, since we're adding two base 2 logarithms, we want to write that as a single base 2 logarithm by multiplying the arguments. So we multiply x times x plus 2. Okay, now that we have a single base 2 logarithm, now we can convert this logarithmic equation to its exponential equation equivalent. The base number 2 raised to the exponent 3 equals the argument x times x plus 2. So we can write the argument x times x plus 2 equals the base number 2 raised to the exponent 3. This equation is just a quadratic equation. So we'll multiply x times x plus 2. We get x squared plus 2x. 2 to the third is 8. We'll set one side equal to 0. We'll subtract 8 from both sides. So x squared plus 2x minus 8 equals 0. We can solve any quadratic equation whatsoever using one of the methods. But it turns out we can solve this one by factoring. So one of the factors is x plus 4. The other one is x minus 2. This quadratic equation has two solutions. One is x equals negative 4, and the other one is x equals positive 2. But remember that we're solving a logarithmic equation. We can tell by looking that negative 4 cannot be a solution to the logarithmic equation because it makes at least one of the arguments negative. It actually makes both negative, but it only takes one argument being negative to disqualify it. So negative 4 cannot be a solution. X equals 2. Well, log base 2 of 2, that's okay. And log base 2 of 2 plus 2, that's also okay. And you can do the logarithmic arithmetic to verify that the 2 really is the solution. But for now, I'll just say that x equals 2 is the solution. This problem is similar to the one that we just did, so I will bypass this one for now. If there's time later, we'll come back to it. This one is a simple equation to solve if you understand logarithms. Log base 3 of 1 minus 5x equals 4. We want to solve for x. X is inside the argument of the logarithm. So we can convert this to an exponential equation. The base number 3 raised to the exponent 4 equals the argument 1 minus 5x. Or you could say the argument 1 minus 5x is equal to the base number 3 raised to the exponent 4. 3 to the 4th is just 81. And so now we can subtract 1 from both sides. We get negative 5x equals 80. Then divide both sides by negative 5, x equals negative 16. And negative 16 is the solution for x, because if you replace x with negative 16, we'll get a positive argument. 1 minus 5 times negative 16 is equal to log base 3 of 1 minus negative 80, which is 1 plus 80, or positive 81. So even though the solution is negative, it makes the argument positive, and it is the solution. Okay, this one is pretty straightforward. Log base 4 of 2t plus 5 equals log base 4 of 9 minus 2t. So that has to mean that the arguments are equal. 2t plus 5 is equal to 9 minus 2t. And we can verify, we can find the solution and make sure that the solution to this equation does not make an argument of a logarithm negative. So if we add 2t to both sides and subtract 5 from both sides, we get 4t equals 4, t equals 1. And when you replace every t with 1, everything works out fine. You'll get log base 4 of 7 equals log base 4 of 7, and that's certainly true. So t equals 1 is the solution. This problem down here, this one's a little different than what we've seen so far today. So let's go ahead and do this. On the left-hand side, we have the natural log of 5x minus 12. On the right-hand side, the natural log of x plus the natural log of x minus 3. So the first thing to do is on the right-hand side, apply the product property of logarithms and write the right-hand side as a single natural logarithm by multiplying the arguments x times x minus 3. Okay, and now that the left-hand side is a single natural logarithm, and so is the right-hand side, now we can say that the arguments are equal. 5x minus 12 equals the argument x times x minus 3. So we need to multiply those, so I'll just go ahead and do that now. X times x minus 3 is x squared minus 3x. We have a quadratic equation, so we'll make the left-hand side 0 by subtracting 5x from both sides and also adding 12 to both sides, and we get 0 equals x squared minus 8x plus 12. And we can solve this by factoring. So one factor is x minus 6. The other factor is x minus 2. This quadratic equation has two solutions. One is positive 6. The other one is positive 2. But up here in the logarithmic equation, x equals 2 makes this argument negative, and that's enough to disqualify it. So x equals 2 cannot be a solution. However, x equals 6 does not make any of the arguments negative, and I'll leave the rest for you to do. You can verify by using logarithmic arithmetic that x equals 6 is really the solution to that equation. Okay, on this one, if a word problem, if $14,000 is invested and earns 7.25% interest compounded continuously, determine how long it will take for the money to quadruple. So let's write down the function. We have all of the information for the function. The initial amount invested is 14,000, so A equals 14,000. And interest is earned at 7.25% compounded continuously. So this is like an exponential growth parameter, 7.25%. So when we apply it to the interest formula, it's A equals 14,000 times e to the 0.0725 times t, where t is the number of years. Notice this has even though the letters are not all the same, it has the form y equals y sub 0 times e to the kt. But instead of using k in our interest formulas, we use r instead, but they have the same function. Now, this is just to point out that this was discussed in an earlier section, whereas this is discussed in section 3.6. But in this particular case, they are equivalent. This is continuous exponential growth. Okay, how long does it take for the money to quadruple? That means to be 4 times the initial amount. So we want to find the value of t when the value of a is 4 times the initial amount, 14,000, and 4 times 14,000 is 56,000. Okay, so to answer that question, we replace a with 56,000. We set it equal to the function 14,000 times e to the 0.0725t, and then we solve for t. So first, divide both sides by 14,000. 56,000 divided by 14,000 is 4. We already know that. That's equal to e to the 0.0725t. And now we take the natural log of both sides. The natural log of 4 equals the natural log of e to the 0.0725t. The natural log of e to the 0.0725t is just the exponent, 0.0725t. And so the answer, divide both sides by 0.0725, the amount of time it takes for the amount to quadruple is the natural log of 4 divided by the annual interest rate in decimal form, 0.0725. So just an observation, hopefully you'll notice we wanted to find the amount of time it took for the investment to be worth 4 times the initial amount. So it's not a coincidence that this is the natural log of 4 times. Okay, the next problem. Suppose $5,000 grows to $6,356.25 in 4 years under continuous compounding. Find the interest rate. Okay, so this is another continuous exponential growth model. Even though this was discussed before section 3.6, it's equivalent to that. Let's write down the function. The initial investment is 5,000. The annual or the interest is compounded continuously. So A equals 5,000 times e to the RT. Well, we don't know what R is, but we are told that when T is equal to 4 years, the value of the investment A is $6,356.25. So in this function, we're going to replace A with $6,356.25, replace T with 4, and then solve that equation for R. Okay, so replace A with 6356.25, set that equal to 5,000, and the e to the 4R, we are replacing T with R, and now we solve for R. Divide both sides by 5,000. We get 6,356.25 divided by 5,000 equals e to the 4R. And now we take the natural log of both sides. So we get the natural log of the left-hand side, 6356.25 over 5,000. That's equal to the natural log of e to the 4R but the natural log of e to the 4r is 4r. And so I'll be a little lazy. I'll just divide every term in all three parts by 4. So the exact answer for the annual interest rate in decimal form is the natural log of this number all divided by 4. And then you can convert this to a decimal number. Just take the natural log of 6356.25 over 5,000 and then divide that whole thing by 4. Okay. In section 3.6, we have some what are called literal equations to solve. Solve this equation for c. So we have the base 10 logarithm of q divided by capital C equals negative t over m times n. Solve this for c. C is inside the argument of this base 10 logarithm. So we can start by converting this logarithmic equation to an exponential equation with base 10. So the argument q over capital C is equal to the base number 10 raised to the exponent negative t over mn. Then we have a couple of ways to go about it. So I'll just start by multiplying both sides by by c. So we get q equals c times 10 to the negative t over mn. And then if I divide both sides by 10 to the negative t over mn, we'll get our answer. But we can also equivalently multiply both sides by 10 to the positive t over mn. Okay, so I'll just do it the first way. Divide both sides by 10 to the negative t over mn. And when we divide the right-hand side by that, we're just left with c. And this is an okay answer, but since the exponent of this term in the denominator is negative, we can write it as q times 10 to the positive t over mn in the numerator and set that equal to c. But either way is okay in this case. Okay, on this one, solve for t. 8 times p sub 0 equals p sub 0 times e to the kt. Solve for t. This is like asking, find the amount of time it takes for an initial quantity to be 8 times that initial quantity. If the initial amount is p sub 0, then 8 times p sub 0 is 8 times the initial amount. So first divide both sides by p sub 0, and we get 8 equals e to the kt. We want to solve for t. T is in the exponent, so take the natural log of both sides. The natural log of 8 equals the natural log of e to the kt. The natural log of e to the kt is kt, and we want to solve for t, so we just divide both sides by k. The natural log of 8 divided by k. So we've seen a number of reoccurring things happen. Try to take notice of those. Okay, so here's an example, sort of a run-of-the-mill type example for modeling continuous exponential growth. For this one, the size of a population at time t equals 0 years was 640. At time t equals 5 years, the population was 720. Assume continuous exponential growth and find the growth constant k. Sometimes you won't see that word continuous. Sometimes it will just say assume exponential growth and find the growth constant k. But usually they mean this model, y equals y sub 0 times e to the kt. Okay, so the initial population is 640, so y sub 0 is equal to 640. And we're told that, whoops, oh, sorry, I'm right. Y sub 0, that's the initial quantity. Then we're told that when t is 5, the population y is 720. So we'll use that information to determine what the continuous growth constant k is, or just the growth constant k. Okay, but first I'll just write what we know. We know that the initial quantity is 640, so I'll just write y equals 640 times e to the kt. And then the second thing that needs to be found, if a model is going to be fully defined, is the growth constant. Okay, so we're given that the value of y is 720 when the value of t is 5. So 720 equals 640 times e to the 5k. Now we just solve for k. Divide both sides by 640. 720 divided by 640, that reduces to 9 over 8. So I'll just write it as 9/8 equals e to the 5k. And then take the natural log of both sides. The natural log of 9/8 equals the natural log of e to the 5k. And the natural log of e to the 5k is just 5k. And then we can divide both sides by 5. So the continuous growth constant k is the natural log of 9/8 divided by 5. Okay, so 9/8 is a perfectly fine number, but you can write it as 1.125 if you want. Okay, so for the part B, to find the amount of time it takes for the population to double, that's like asking for the doubling time. We need to write the function y equals 640 times e to the, I'm going to write it as the natural log of 1.125 over 5 times t. Okay, so how long does it take for the population to double? So replace y with 2 times 640, or 1280. 1280 equals 640 times e to the kt, or k is the natural log of 1.125 over 5 times t. Divide both sides by 640. 1280 divided by 640 is 2. So 2 equals e to the kt, e to the natural log of 1.125 over 5 times t. Now take the natural log of both sides. So we get the natural log of 2. And I'll do a shortcut here. The natural log of e to this exponent, or the natural log of e to the kt, is just kt. So the natural log of 2 is equal to the natural log of 1.125 over 5 times t. And then to solve for t, we can multiply both sides by the reciprocal of this number. That is, multiply both sides by 5 divided by the natural log of 1.125, and we get 5 times the natural log of 2 divided by the natural log of 1.125 equals t. Hey, this is the exact answer. It's measured in years, so if you want a decimal approximation, then just key those numbers into a calculator. Okay, we can answer this one in one step if you've sort of been noticing the patterns that show up. Find the amount of time it takes for the population to be 5 times the original size. So that amount of time is the natural log of 5 divided by k. So, the natural log of 5 divided by k is the natural log of 1.125 divided by 5. This could be written as 5 times the natural log of 5, all divided by the natural log of 1.125. So if you want to work it out step by step, like the previous example, you can do that. Okay, so this one is sort of the same process. It's just this time we have exponential decay. At time t equals 0, suppose that you acquire 2 kilograms of plutonium-238. If the half-life of plutonium-238 is 87.7 years, write a function of the form q of t equals q sub 0 times e to the kt to model the quantity of the sample after t years. So this is just by telling you that the model should have this form, we know that it's continuous exponential decay because of the e to the kt. The initial quantity is given to be q sub 0, and we're told that the half-life is 87.7. So all we have to do is determine what the decay constant k is. Okay, so we can note that when t is 87.7, q of 87.7 is equal to 1/2 of 2, or 1 kilogram. Okay, so what do we do now? Well, we replace q of 87.7 with 1. The initial quantity is 2, and so it's 2 times e to the 87.7 times k, right? Because this is just doing what the half-life tells us. So we want to solve for k. So first divide both sides by 2, we get 1/2 equals e to the 87.7k. Then take the natural log of both sides. The natural log of 1/2 equals the natural log of e to the 87.7k, which is just going to be 87.7k. And so the decay constant is the natural log of 1/2 divided by 87.7. Remember a few days ago when we did this, we noted that for continuous exponential decay, the decay constant k is the natural log of 1/2 divided by the half-life. That's what we have here, because we're given from the start that 87.7 years is the half-life. Okay, so we're rapidly losing or running out of time. I'll just write down the complete model in part B. Q of t equals the initial amount 2 times e to the kt, but the value of k is the natural log of 1/2 divided by the half-life, 87.7 times t. To answer part B, just replace t with 43 and so on. Okay, I want to get to this problem. Couple of problems. So this says the graph of a one-to-one function appears below. Graph its inverse function on the grid to the right. Okay, notice on this graph, there's below the x-axis, there is a vertical asymptote, x equals 1. So that means for the inverse is going to have a horizontal asymptote to the left of the y-axis, y equals 1. And we have 3 ordered pairs on the graph of the function. So we can plot the points on the inverse by interchanging those. So this point on the graph of the one-to-one function, 3/2 for x, -1 for y. So interchanging x and y, so -1 for x and 3/2 for y, we get this point. So when we interchange, this is -1 3/2. Okay, another point on the graph of the original function is the ordered pair 2, 0. So on its inverse, we have 0, 2. And then on the original function, the point 3, 1. So that means on the inverse is the ordered pair 1, 3. And then the graph is going to have the same shape, but just in a reflected sort of way. So the graph of this function is something like this. So this could be the graph of a logarithmic function, and this could be the graph of its inverse, which is an exponential function. Okay, the next one is there's a little bit more to do, but it's not too hard, really. On the graph of a one-to-one function appears below. Graph its inverse on the grid to the right. Okay, so this could be the graph of a rational function. I don't have a formula for it, but looks like one of those run-of-the-mill types of rational functions. So notice on this graph, we have a horizontal asymptote y equals 2. That means that on the graph of the inverse, x equals 2 is a vertical asymptote. Okay, on the graph of this function, we have a vertical asymptote, x equals -1. So that means that on its inverse, we have a horizontal asymptote of y equals -1. Okay, then we can figure out what the rest of the graph looks like by interchanging the ordered pairs that we see. This point, -2, 3, on the graph of this function, corresponding to that on the inverse is 3, -2. That's down here. And we can graph this part on the inverse. It's just going to follow the same sort of pattern. It's just a reflection of that. And then this point, a couple of more points. This point, 0, 1, corresponds to 1, 0. That's right here. And on this function, -1/2, 0, corresponds to 0, 1/2, which is this point. And then we can sketch the graph to do that. So this is a graph of the inverse of that. Okay, we're out of time. So keep working on Chapter 3 material, and we'll have a test. There won't be a YouTube Live on Friday, but I'll send information about the Zoom meeting for the test on Friday. That's all for today.